Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be doing unit number 9, lesson number 2, the parametric form of a line. So you've worked with a lot of linear equations, you've done a lot with y equals mx plus b, with point slope form, y minus y1 equals m times x minus x1, lots of stuff like that. Today what we're going to concentrate is on how to use parametric equations to accurately represent all the points on a line. Now in 2-space, this might be somewhat questionable, let's say. But in 3-space, the only way really of representing a line is to use parametric equations. So let's begin. All right, we're going to start with the simplest of all lines, horizontal and vertical. Now remember, when we give parametric equations, what we're doing is we're giving an equation for x, we're giving an equation for y, both in terms of a third variable, which we almost always call t. All right? Now, what we want to make sure we do is give a description so that we get the points that we know are on the line. So, for instance, we know y equals 6, right, is a horizontal line, 1, 2, 3, 4, 5, 6 units. Whoops, I missed it. But that's y equals 6, right? We want something that gives us all those points. So points like 0, 6 and 3, 6 and negative 2, 6, right? Whatever we do has to give us those points. So watch how easy this will be. I'm going to let x be equal to t, and I'm going to let y be equal to 6, and I'm going to say that t has to go from negative infinity to positive infinity. And there's my parametric setup. That's it, right? So it's kind of cool because you could say, well, all right, like t equals 2, right? That's a value between negative infinity and positive infinity, and what it would give me is this point, right? You could say t is equal to 10, and it would give me this point, 10 comma 6, right? And that's what we need, right? We need points that are on this line. So that's it. Why don't you pause the video really quickly and write the equation or the equations that represent that vertical line that we have in part B. Okay, pretty easy as well, right? This vertical line, what we've got going on here, right, is we've got 1, 2, 3. So, whoops, we want some parametric setup that gives us all those points. And it's going to be very easy. We're going to let x equals t. We're going to, whoops, no we're not. Haha, sorry. We're going to let x equals negative 3. We're going to let y equal t. And we're going to let t go from negative infinity to positive infinity. Now, I want to really emphasize something, all right? These answers are not even close to unique. There are tons of different equations that would allow us to do this. Some that you might not even think about. So strangely enough, this is going to be a weird alternative. What? Watch this. Watch this. This will be cool. Let's say I had x equals negative 3, and I had y equals negative 2 times t, and I let t go from negative infinity to positive infinity. Right? This would also work, right? Because every point I want, I can get for some value of t, right? So let's say I wanted the point 6, I can't get that point. Let's say I wanted the point negative 3 comma 6, right? I would get that point if t was negative 3, right? Because x is always negative 3, and then y would be negative 2 times negative 3. That would give me 6. Now don't get me wrong. If we're talking about motion, these two are the same path, but they aren't the same motion, all right? But that's not what we're dealing with today. We're just trying to come up with equations that give us the entire answer, all right? That give us all the points that lie on this curve. So let's take a look at one that's a little more challenging. In exercise 1, we wrote the equations of lines, which are infinitely long. In number 2, we're going to write the equations of a line segment. So take a look at this thing, right? I need to give a set of equations along with an interval for t that gets the job done. So what do I know? 1, 2, 3, 4, 5. Right? What I know is that I've got a line segment that goes from positive 5, comma, negative 2 up to positive 5, positive 5, right? Now this is definitely a segment of the vertical line x equals 5, right? It's a portion of it. So what should I write down? Think about this. See if you can write out a system. Now remember, you need an x, you need a y, and you need an interval for t. Okay? So try to do that. While you're doing that, I'm going to do a little erasing. There we go. All right, let's talk about it. It's actually pretty simple. Now again, there's a million different options. There's actually more than a million. And what I want to make sure you do is not only to take the one that to me is obvious, but also ones that are not obvious. So let's do this. Let's make x 5. No matter what t is, x is 5. We're going to make y t, and then we're going to make t go from negative 2 to positive 5. There's a good system. Right? That's good, right? Because that'll start us at the point 5 comma negative 2, and it'll end us at the point 5 comma 5, and we'll get every point of the form 5 comma whatever that lies in between. Now, there are many others. Let's just say for a second, that we got to have this, right? It's got to be x equals 5. Hard to avoid that. Let's leave the y off, and let's say the t goes from 0 to something else. Let's say that t represents time, and I want it to start at 0. So what do I make y? Remember, y is that we've got to start at this point. We have to start at this point, and we need to end at this point. Actually, I suppose we could go the other direction as well. I didn't really specify a direction. I apologize for that. But let's assume that we're starting here and we're ending here, right? Well, then what would this have to be? It would have to be t minus 2, right? Because then if I put 0 in for t, y will start at negative 2. And what will it go to? Think about that for a minute. Pause the video if you need to. All right, it'll go up to 7. Notice that the change in t, right, the delta t for both of these is still 7, right? If you want, we need to have 7 seconds to make this trip, right? But as long as we start at 5, negative 2, and we end at 5, 5, and our x is always 5, it doesn't matter what we do in between. All right, I'm going to clear out this text, so copy down anything you need to. All right, here it goes. Okay, let's keep going. So that was horizontal and vertical. Now, of course, what we really want to concentrate on are slanted lines. All right, so let's take a look at exercise number 3. It says, given a slanted line in parametric form, x equals negative 1 plus 2t, and y equals 5 minus 3t, do the following. First, we're asked to graph the line on our calculator, and then, by using the table, calculate the slope of this line, and also verify that the point negative 1, 5 lies on this line. Okay. Well, so this is very calculator driven, so what I'm going to do is I'm going to bring out the TI-84 plus at this point. Let's do that. All right, we have it. So remember, what we're going to do is we're going to be in parametric mode. Let's make sure we're in parametric mode by hitting the mode button. Checking. All right, if we're not in parametric, we should get there. Now let's get out of there. Let's hit y equals. Clear out any equations you might have in there. And in x1 comma t, let's put in negative 1 plus 2t. Enter. In y1 of t, let's put in 5 minus 3t. Enter. Now we have to think about our window. Now remember, this is a line, so what we want to do is we want to make sure that we're graphing it with a sufficiently large window. It's kind of hard to know what our t interval should be, but why don't we go negative 10 to 10? Can't possibly hurt, right? Y and x, why don't we just stick with that standard window? Negative 10 to 10 in x, and negative 10 to 10 in y. And let's graph it. There it is, right? It's not too bad. In fact, we can sketch a little graph of it. And what it ends up looking like? Something like that. Yeah, with a little artistic liberty. Right? A little artistic liberty. All right. So, now let's take a look at the table. We haven't really looked at tables with parametric equations yet, so let's go over to our table in our calculator. All right. Now it asks us to do two things. It asks us to calculate the slope of the line, and also to verify that the point -1, 5 lies on the line. Okay, and we'll kind of get to this point in a little bit. But it's pretty easy to actually calculate the slope of the line, right? What we need is 2 points. In fact, why don't we take the point when t is equal to 0, because that's the point we wanted to verify, that's 1, 5. Why don't we take the point when t is equal to 1, because that's going to be 1, 2. Pretty easy now to calculate the slope of the line, which hasn't changed at all. It's delta y divided by delta x, which is 2 minus 5 divided by 1 minus -1. Gives us -3/2. All right, so two things I wanted to do: verify that that was on the line and come up with the slope. And the reason I wanted to do that is I wanted you to look at this generic form for a slanted line. You see, because we can see two things in it very quickly. We can see a point that lies on the line, but we can also see its slope. Do you notice the slope is -3 to 2? Okay? And I really want you to understand this, okay? So let's pause for a minute and talk about this. Let's take x equals -1 plus 2t, and let's take y equals 5 minus 3t. This is very important and it's tricky for kids. You see, both of these all by themselves are linear equations, right? That's linear and that's linear. So they have their own slopes. For instance, delta x to delta t, well, that's +2. Delta y to delta t, well, that's -3. Now, what do these two things mean, right? Well, what they mean is that when there's a change in t of 1, the change in x is 2. And when there's a change in t of 1 here, the change in y is -3. So what's cool is that a change of t of 1 results in a delta y to delta x of -3/2, and then that's our slope. So it's kind of weird. There's really three slopes in this problem. There's the rate that x is changing with respect to t, there's the rate y is changing with respect to t, and then there's the ratio of the two rates, which actually gives us how fast y is changing compared to x. Fair enough? I'm going to clear out this text, so copy down anything you need to. And let's summarize all of this, right? The parametric form of a slanted line. So if we know a point that the line passes through, and we know a vector that the line is parallel to, we can say that the line has the equation x equals x1 plus at, y equals y1 plus bt, where t goes from -infinity to +infinity, and then we can easily write the Cartesian, very important term, the Cartesian equation, which just has y's and x's in it, in that point-slope form. We can always find the slope by finding the ratio of b to a, and then we have a point that lies on the line. All right, so we're going to get some practice with these ideas in the next problem. All right, let's take a look. It says a line has a Cartesian equation of 2/5 x minus 8. Find a parametric representation of this line and graph it on your calculator to verify. All right, well, there are so many different equations, One thing that we absolutely need is we need a point that lies on this line. All right, so a point that lies on the line. Now, as you know, of course, there's an infinite number of those, which means that the equation can be all sorts of different. One point that's easy is 0, -8, but there's lots of them. For example, 5, -6 lies on this line. But whatever, right? Let's use this one. All right, so what we can now say is we can now say that x would be 0 plus 5t, and y would be -8 plus 2t. Now again, the 5 and the 2 come from the fact that the slope is 2/5, and that's really delta x, whoops, that's really delta y divided by delta t divided by delta x divided by delta t, right? So I use the delta x divided by delta t as my 5, delta y divided by delta t is 2. All right. In terms of verifying it or graphing it on the equation, that's pretty much easy enough, okay? And I'm going to not waste your time right now. Why don't you go back in, place these two equations in. Of course, we really should finish it by saying that t goes between negative infinity and positive infinity, right? What I'd like you to do on your own is put this into your y equals, right? Maybe use negative 10 to 10 on your t, and just verify that it's got a y-intercept of negative 8 and a slope of 2/5. All right. I'm going to clear out this text, so write down anything you need to. Okay, let's move on. Okay, exercise number 5. A line in 2 space has a parametric representation of negative 6 plus 2t and 3 minus t for t greater than negative infinity less than infinity. Letter A says give a point that this line must pass through. Pause the video and do that. All right, there are so many answers to this question, so many, right? All you have to do is pick a value of t. Any value of t, substitute it into that equation, and you're going to get a point that the line passes through. But if you chose the point t equals 0, it's very simple to see that the point negative 6 comma 3 lies on this line. But that's one of many. For instance, let's just say I took t equals 3. What would I get? Well, x would be negative 6 minus 6, which would be negative 12. Y would be 3 minus 3, would be 0. So that also lies on this line. Again, we only need one, so this is as good as any. What is the slope of this line? Again, pause the video now and see if you can answer this question. All right, let's go through it. Well, you could use 2 points and calculate the slope, but again, the slope is going to be the slope of the y line divided by the slope of the x line. The slope of the y line is negative 1. The slope of the x line is positive 2. So the slope of this line is negative 1/2. Finally, giving a Cartesian equation for this line is a piece of cake. There's many different things we could do. If we use point-slope form of the line, y minus y1 equals m times x minus x1. It's easy to grab either one of these 2 points. Let me grab the first one and do y minus 3 equals negative 1/2 times x plus 6. All right, that's it. Letter D says graph the line in function mode and parametric mode to verify your answer. See, one of the things that's unfortunate is it would be really nice to be able to have a graphing utility that allowed me to put in this parametric system of equations, then this Cartesian equation, and compare the two. The best I can tell you right now, and again, I don't want to take your time up, but the best I can tell you right now is graph the parametric one, see what it looks like, graph the Cartesian one with using the same window, see what it looks like, and they're going to look the same. It'd be great if we could graph them at the same time, though. Okay, I'm going to clear out the text, so copy down what you need to. All right, let's move on to the next page. Whew, all right, here we go. A particle moves from the point 6, 2 to the point 0, 10 along a straight line segment. Find a parametric representation for its path. Be careful, you must specify an interval for the parameter t and make sure the motion is in the correct direction. And this is tricky. This is probably the hardest thing that we do in this lesson. So let's see what we can do. I want to really try to understand what's going on here. We've got a particle moving from 1, 2, 3, 4, 5, 6, 1, 2. We have a particle moving from 6, 2 to 0, 10. 3, 4, 5, 6, 7, 8, 9, 10. If you will, point A and point B. I think I'm going to use this to help me really draw it. All right. So I have to do that. I got to make sure it goes in the right direction. I got to make sure I have the right interval. So here's the thing, and this is really important to me. If I give my students a problem like this, I need their answer, because there's many different answers that are correct to really do three things. I need at the beginning of the time interval for the particle to be at point A. I need at the end of the time interval for the particle to be at point B, and I need it to stay on the line segment the entire time. Besides that, there are many different ways to do it. So let's do something. As we move from 6, 2 to 0, 10, let's figure out a couple things. Let's figure out our displacements, delta x and delta y. All right. X goes from 6 down to 0, so delta x is negative 6. Y goes from 2 to 10, so delta y is positive 8. You probably can already see a little bit about where I'm going with this, right? But let's give it a little bit further. Let's say, right, that we have x equaling to 6 plus negative 6t. Let's put y at 2 plus 8t, right? Now what's nice about this is that we know in a certain sense it's going to work, right? Because we know we've got the right ratio of the change in y to the change in x, and in the right direction. But we still need an interval on t, all right? So I want you to think about this really hard and see if you can figure it out. All right. Well, to make sure that we start at point A, t has to start at 0. And to make sure that we end at point B, t has to end at 1. In other words, delta t must be 1. And if delta t is 1, well then delta x will be negative 6, and delta y will be positive 8, and exactly what we need to have happen will happen. So this is perfectly acceptable. Now, that being said, what a lot of people will do is they'll work out the slope of this line, right? And they'll say, the slope is 8 to negative 6, which is negative 4/3. All right? So some people will do this. Not that. Some people will do the following. Now the good thing is that it continues to have the right slope, which is a 4 to negative 3 ratio. But what would be t now? And I really want you to think about this a little bit. What would be t? Lowest level is 0, but what's our highest level now? It would have to go all the way to 2, right? In order to have this set of curves end, and that's the key, end at point B, 0, 10, t has to go all the way to 2, right? Do you see that? We could do all sorts of things. For instance, we could take this thing and we could rewrite it as x equals 6 minus 12t, and y equals 2 plus 16t. And again, the slope's correct, 16 to negative 12. But now, t would just go from 0 to 1/2, right? So there's no real cut and dry way of doing this, and if there is, I'm going to resist it because I'd like you to kind of think about this, right? Think about your delta t, think about your span of t, think about your slopes and stuff like that. But it's not too bad. So copy down what you need to. I'm going to clear out the text. All right. So that was lines. That was lines in parametric form, not too bad. And we're going to revisit them when we do a little bit more with three-dimensional motion and geometry. But for right now, that's going to be it for lines. And we'll pick up with parametric forms of other types of equations tomorrow. All right. So for now, just wanted to remind you that this is an Arlington High School Math 4 Honors lesson, and I'm Kirk Weiler. Until next time, keep thinking and keep solving problems. Thanks for joining us.